Okay. So constraint convex problems. We talked about last time. Well, this X is restricted in a closed convex set. And the first algorithm we introduced the Frankfurt algorithm. The main step of the algorithm is to solve this constrained linear problem. Now, this linear problem, the objective function is linear in X, and it depends on the gradient of the function at your current iteration. It's gradient f at xt. And then this is we need to solve this, minimize this linear function over the constraint set. Okay, suppose we can do that. Suppose we can do that and find the minimizer yt. The next step is a convex combination between xt and yt. Okay. So the key is to solve the second step. And last time we showed that basically the second step can be understood as find a direction that is find the update direction within the constraint set that is negatively correlated with the gradient. Okay. Because imagine if there's no constraint, then we can just do gradient descent by following the negative gradient. But here, due to the constraint, negative gradient may be out of the constraint. So we find a direction that is negatively correlated with the gradient. Yeah. So the key is to solve this linear optimization problem over a convex constraint set. That is line 2. This method is appearing when this the second line, the second step is can be computed easily. Okay. And the step size rule we typically use is this one. This is a theoretically guided step size. We will show it very soon. It's 2 over t plus 2. Okay, and a very interesting example is this the following problem. We want to minimize such a negative quadratic function. We want to minimize this quadratic function subject to the constraint. Well, the L2 norm of x is less than or equal to 1. This is a convex constraint. This constraint set is a convex set because it is a Euclidean ball. It is a ball in the Euclidean space. So that ball is a convex set. And the interesting part is that here we assume this Q is positive definite. Therefore, because of that, we know that X transpose QX, this function is a convex function because Q is positive definite. However, here we have negative sign. This negative sign makes the entire objective function concave. It is a strongly concave function. So this problem is to minimize a concave function over a convex constraint set. It falls into the non-convex optimization category because typically we talk about typically we only talk about convex functions, right? F is convex. But here, this example shows that Frankfurt can also be applied to solve non-convex problems. this is minimize a concave function. Now let's apply the Frank-Wolf algorithm to solve this problem. Okay. To solve this problem. Again, the key is to solve the second step, this linear programming problem. So let's write it down here. Is to minimize this linear objective function over the constraint set. Now the constraint set is over the unit Euclidean ball. Now, if you look at this, the solution is actually simple and analytical. Basically, you look for all the vectors have unit norm that is mostly negatively correlated with the gradient. And because the Euclidean ball contains all the directions, right? It's a symmetric ball in over that covers all the directions. So the minimizer x is simply the scaled negative gradient. This YT is simply what? It's simply negative gradient. Because I know the negative gradient is mostly negatively correlated with the gradient, right? So it gives me the minimum value of this dot product. But I need to satisfy that constraint, so I just normalize it. This is the vector. This is the negative gradient vector divided by the length. Right? So normalize the negative gradient. You can see it has unit norm. Right, the length, because of this normalization factor, it has unit norm, and it is negatively correlated with the gradient. Right. So this optimization problem has a very simple solution. So this is our YT. This is our YT. And then let's plug in the gradient formulation. Gradient of f is basically q times x because it's quadratic. It's negative q times x, and the negative sign cancels with this one, so we only have qx over the L2 norm of q times xt. So this is our expression, analytical expression for YT, when applied to solve this problem. And now, once we have YT, the third update is to do a linear combination between xt and YT. So just plug it into the third update, and we have the following update loop. This is the update loop between xt and xt plus 1. And of course, we need to specify the step size eta t in practice. And we can check that the best eta t for this specific problem is actually 1. Okay. So how do we search for the best eta t? We can search by solving this problem. So I plug in the expression of xt plus 1 into the objective function f. And because this xt plus 1 depends on the step size eta, so I search over eta. I search between 0 and 1. I'm trying to find an eta between 0 and 1, so that makes xt plus 1 achieves the minimum value, the minimum objective value. It turns out this problem can be solved analytically just by simple linear algebra. And the solution turns out to be 1, very simple. But once you plug in eta t equals to 1 back into the update rule, now this becomes 0. This becomes 0. So xt, the overall update rule for the Frank-Wolf algorithm is simply this recursion. So xt plus 1 equals to q times xt, and followed by a normalization. And this is essentially the power method. This is a very classic method used to compute the leading eigenvector of a matrix. Okay. So basically, for this method, every time you just multiply so you want to find a leading eigenvector of q. Now every time you just multiply q by xt and just normalize it, and you have the next xt plus 1. And you do this again and again. Eventually, this xt will converge to the leading eigenvector of q. So this classic power method can be viewed as the Frank-Wolf algorithm, right, applied to solve such a constrained quadratic optimization problem. Okay, this is a very nice connection between power method and the Frank-Wolf algorithm. Now let's talk about the convergence guarantee for this Frank-Wolf algorithm. Okay. So let f be a convex and a smooth function. We have considered this class of functions in the previous lectures as convex and smooth function. And then if we choose such a step size and apply Frank-Wolf algorithm to solve this problem, right, with such a step size, then we can have the following convergence rate. The function value gap at step t is bounded by a constant divided by t plus 2. So it's roughly 1 over t. Well, this constant depends on the smoothness parameter L and the dc square. Well, dc is like the diameter of your constraint set. Okay. And here we assume that the constraint has a bounded diameter. This is the definition. The definition of dc is the maximum, like the pick any 2 point that has the longest distance in the constraint set, right? So it is called the diameter. So so of course we can, in this result, we can only deal with bounded constraint sets with bounded diameter. Therefore, this result applies to closed and bounded convex constraints. So we call those constraints compact constraint sets. And because convergence rate is roughly 1 over t, so this algorithm can achieve an epsilon accuracy within roughly 1 over epsilon iterations. This is very similar to the performance of gradient descent applied to convex and smooth problems that we discussed in the previous lecture. But there we don't have constraint. It is an unconstrained convex and smooth problem. But here is a constrained convex and smooth problem. And you can see that even with constraints, the iteration complexity is still the same, otherwise the same as the gradient descent for unconstrained problems. Okay. Now let's look at the simple proof here. So the proof again starts with this what we call smoothness inequality. Remember that if f is a smooth function, it satisfies this inequality for any arbitrary 2 points. And here we specify the 2 points to be xt plus 1 and xt. You will see this step frequently in many of the convergence analysis. This is basically to characterize the optimization progress between 2 consecutive iterations. Now we apply the step size update rule, xt plus 1 minus xt. Now, if you go back to the Frank-Wolf algorithm, right, from the line 3, you can see xt plus 1 minus xt. If you move 1 xt from right-hand side to left-hand side, that is negative eta t times xt minus yt. Right? So you just plug in this. So this is basically eta t times yt minus xt. Right? Replace it. And for the last term, you also do the same thing. This part is just the eta t square times the distance square. But we assume that x and y. So first of all, x and y are both of them are in the constraint set, and we assume the constraint has a bounded diameter. So this term, this distance term, will be bounded by dc square. Okay, so it's a constant upper bound. Yeah. There's an I need to make a comment here. In order to apply this bound, you need to make sure that both xt and yt are within the constraint. Right? Because this dc is like the maximum distance between 2 points within that constraint. Right? So x and y must be in C. So you need to first argue that these 2 parameters generated by the algorithm will always be inside the constraint. And in fact, it's not hard to see. First of all, yt is the solution to this constraint linear programming, right? So yt must be in the constraint set C, because the problem is defined to be within the constraint C, constraint set C. So yt is guaranteed to be in C. Now, assume you start with x0 in C. Okay, then the third line. This is a convex combination between xt and yt. If xt is in C, yt is in C, then we know by convexity the convex combination is in C. So this proves xt plus 1 is in C, right? And you do this argument iteratively, you can show that starting from the first iteration, afterwards every time xt and yt will be staying inside the constraint set. Okay, so so here we skip some of this argument. Okay, then you can say that this can be bounded by the diameter of the constraint set. Okay, and then you just put everything into these terms. This simplifies to the following term. Okay. Now what happened next is that I look at this inner product term. I claim that this dot product, this inner product, can be upper bounded by replacing yt to be x star. Well, x star is the minimizer of this constraint convex problem. right? I assume X star is one of the solution of this problem. Now I claim that this dot product has a lower value than this dot product by replacing YT by X star. This is because YT, by definition of the Frank-Wolf algorithm, is the solution of that linear programming. Right? YT minimizes such a inner product term within the constraint set. So of course, I can replace YT by any other point in the constraint set. And because it is a minimizer, so the objective value will be lower than the following one, right? So it's by this condition. And in this case, X star, because X star is the solution of this our original problem, so X star is guaranteed to be in C. By default, it must be inside C. So I can replace that with X star, and this is a less than or equal to the upper bound. Then I can get rid of YT. Right? I can replace YT by a fixed point. And then I can apply convexity of function f. So this dot product can be upper bounded by the difference of the function value, because the function is convex. Right? This is the definition of convex functions. So we have this inequality. Right? So eventually you can transform this dot product into a difference of function value terms. And this is the function value term that we want to check, right? Something about your current function value and your minimum function value. Okay. Then the next step is this is the key recursion that we need. Then we just define delta t to be the function value gap at t, right? And then this is basically the left-hand side is delta t plus 1 minus delta t. And this is negative delta t. Right? You just replace those notations with delta t. Then this recursion can be written in this way. Right? This is a very simple recursion on delta t. And you can go over a very simple induction to prove this, to get an upper estimate of delta t. Okay, so yeah, I think I will not go over details. You can just check, just argue by induction. Okay, well, this eta t is you need to use the definition of this eta t. Okay. So this is by induction, or you can also work out this recursion by yourself. You can just unroll it and do some calculations, but that will involve some additional computations. Okay, but induction is kind of a lazy solution once you know the solution, you know the final solution. Okay. But this is how we get the key recursion for this Frank-Wolf algorithm. Okay, yeah. So this is the first approach, Frank-Wolf algorithm. So this approach works very well when this linear programming can be solved very efficiently. Now the second approach that we want to talk about is called the projective gradient method. It is something even more straightforward compared to Frank-Wolf. And the idea is very, very simple. In the previous lectures, we talked about gradient descent. So this is the update for gradient descent, right? So xt minus the gradient times the step size. But we know in the constraint setting, the issue is that if you do gradient descent, it is likely that your next update may go out of the constraint set, right? That will violate the constraint. So a very simple idea is that after every gradient update, I just use some operations to pull it back onto the constraint set. And this can be done by using this projection operator. Okay. So this projected gradient descent is a very straightforward extension of gradient descent. It's like we first do a gradient descent update. Okay. And after that, for this new vector, I project it onto the constraint set. Now, if this new vector happens to be inside the constraint, then the projection does nothing. It's just itself. Otherwise, if the new point is outside the constraint set, then the projection simply finds the point that is closest to the constraint set. Okay. So this figure illustrates this idea. Suppose you start from this point, x0, which is in the constraint set, and now you follow gradient descent. Okay, this is the gradient, negative gradient direction. After that, obviously you are out of the constraint. So what you do is to do a projection, project it back onto the constraint set. Okay. And this projection simply finds a point in the constraint set that is closest to this point. Right? This is called projection. Now after that, you continue to do a gradient descent update. And again, it may happen that you go out of the constraint again. So every time you just pull it back onto the constraint through this projection operation. And mathematically, this projection operator is defined as following. For every point x, the projection onto a convex set C is defined as the following optimization problem. So I fix this x, and I look over all the points Z over C in C that has the shortest distance to x. It's a very natural. It's essentially how projection is defined. We look for the point in the constraint set C that is closest to your reference point. Right. We are familiar with the projection concept over hyperplanes. This is how we project a point onto a hyperplane. But for a general convex set, right, it may not be a linear, it could be a nonlinear set. You can still find a closest point. This point is the closest. So this is projection of x onto C. That has the shortest distance. Okay. And you can see to implement this algorithm. So first of all, we haven't talked about the convergence guarantee of this algorithm. But to implement this algorithm, we need to implement gradient descent step. That is inside this big parenthesis. After that, we need to do a projection. Right? So to implement this algorithm, we need to find a way to implement this projection. And this depends on the specific problem. For different sets, the projection may be simple. It could be very complicated. So it really depends on the problem form. Yeah, and then this is a illustration of the projection operator. You have a constraint set C that is convex, and let's say you want to project X onto this point. So by definition, this is a point that is closest to your reference point X, right? And we call this the projection of X onto C. Okay. And there's another equivalent definition about this projection. Okay. So if you go to the previous slide, the projection is defined in terms of the minimum distance. You find a point Z in the set C that is closest to your reference point. But equivalently, this point can also be described by the following inequality as the projection theorem. Now, this theorem says this. Let C be a convex set. Then XC is the projection of X onto C, right? Then a point XC is the projection of X onto C if and only if the following condition holds. The following condition says that for any other point Z in C, Z minus XC is negatively correlated with X minus XC. Now, if you look at this figure, XC is the projection point, right? Now, X minus XC is this vector. It's going outside. Now, the theorem says that if XC is a projection, then for any other point Z in this set, these two vectors always has a negative, are always negatively correlated, like their angles is bigger than 90 degrees. And you can verify. Now, an intuitive understanding is that if you project this point onto the set, right, it is like you are looking for a point where the tangent line is perpendicular to X minus XC, right? And this is exactly 90 degrees. But this is a convex set, so it is like all the sets are on the right-hand side. All the points are on the right-hand side. So whatever point you pick, right, you pick any arbitrary Z, and this will always form an angle that is bigger than 90 degrees. Okay, because this is the boundary case. This is the tangent line that forms a 90 degree perpendicular. Everything is on the other side. And this is a very useful tool in the convergence analysis. We will see it's a very powerful tool. It is equivalent to say that XC has the minimum distance. Okay. Yeah. And this is to further specify that, apply that the previous result to the projected gradient method. Okay. So let's say you start from xt. This is the point you obtained from the previous iteration. Now you do one gradient descent, and you achieve. Now you arrive at this point, right? This is the gradient descent update. Sorry. This is a gradient descent update. Okay. Now, it may happen you go outside the constraint point, but then you do a projection. Right? This projection gives you the next point, xt plus 1. Okay, so this is the two-step process. Gradient descent, going back, I do a projection. Okay.
What's a real-world example of a reason you would want to put a constraint on your problem?
Yeah. A very simple example is that normally you don't want to search over the entire space. Like the entire space goes to infinity. Like in many cases in your problem, the optimization parameters that you are looking for, based on your prior knowledge, they may be within a certain constraint set. For example, I believe they are between 0 and 1 and 1, or for probabilities, they are between 0 and 1. Yeah. So if you have some prior knowledge about your problem, if I'm looking at something in a power grid, maybe those voltages may be it's between 100 and 200 based on my prior knowledge, right? They will not go beyond too far. And based on that, you can put some constraint to your problem to reduce the complexity, right? Okay. And we will see many, there are many examples come later that about different constraints in different applications. Yeah, question.
When this algorithm finally converges to the optimal solution, is there a world where the projection ends up taking away from the optimal solution and then back towards it, and away from it and back towards it, and you kind of end up bouncing in between?
That's a very good question. I think in the end, it will converge to a kind of equilibrium point. Well, if you start from that point, going out and do a projection, you will get back to exactly the same point. That's how we call it converges, right? After, if you start from solution and run this algorithm for one more iteration, it goes back to the same point. Yeah, and that's called as kind of stationary point in this sense. Yeah, and so this is the illustration figure. So let's consider so next we will look at the convergence guarantee for this projected gradient method. Okay. But to simplify the discussion, let's first look at the strongly convex and smooth problems. So let's summarize the problem setting first. So minimize f subject to a constraint, and here we assume f is mu strongly convex and L smooth. Now we have seen this before in the previous lecture, but there we don't have constraint. F is mu strongly convex and L smooth, and C is a convex constraint. Okay. The first very interesting and very fundamental result is the so-called non-expansiveness of a projection operator. Projection onto convex sets is non-expansiveness in the following sense. You pick any 2 points x and z. Okay. Now these 2 points will have a distance between them, right? It's L2 distance. Now, if you project these 2 points onto a certain convex set, let's say X I projected onto this set, and I get the projection point is PCX. Okay, Z onto this set is we get PCZ. Now this result shows that the distance between these two projected points is always smaller than or equal to your original distance. So this is called non-expansive. So after projection, your distance is always smaller. It's always smaller. And yeah, I did not prepare for the proof of this one, but maybe you can check. You can check Wikipedia. I think there are some simple proofs on this one. And later we will have a generalization of this result when we talk about other operators. But think about a simple case. Think about projection onto hyperplanes. There it is obvious, right? You have 2 points. Now you project them onto the hyperplane. Now what happens is that maybe imagine this point is higher than this point. Okay, so I can, right? So this is the distance between your projected point. Now, and this one I can move it to here because they are parallel with each other. Now this is the distance of your projected between your projected point, but this is the distance between your original point, right? So apparently it's smaller. It's smaller because it's in a triangle with 90 degrees. So it is obvious in this simple case, and this result simply is a simple generalization to the convex case in general. Okay, so these will be useful. Okay, so the convergence guarantee for projective gradient descent is the follows. Okay. So this result is to apply projective gradient descent to solve a strongly convex and smooth problem, right, with a convex constraint. Let's put everything together. So if function is mu strongly convex and L smooth, and if we choose the step size 1/L, then the projected gradient descent satisfies the following convergence rate. Right? It's very similar to what we have seen before. So this is the distance to the minimum point. It diminishes to 0 at a geometric rate. Okay, the right-hand side is something. This is a geometrically diminishing term, okay? And then the other term is a constant distance. So it shows that projective gradient descent can achieve a geometric convergence for this type of constraint optimization problems. Yeah, it is slightly weaker than the convergence guarantee of theorems 3.5. So 3.5 is for gradient descent applied to strongly convex and smooth problems. Well, we don't have constraint there. The only difference is that we don't have constraint. And it is weaker in the sense that this number inside this number, this coefficient, is slightly bigger, but it is still less than 1. So the difference is not very big. Okay. So this is a very interesting result. It seems that even if we have constraints, this algorithm can still achieve a very fast convergence. So let's look at the proof. The proof is actually very simple, very interesting. Because the projection operator is very hard to characterize for different problems. The projection operator may take very different forms, right? We don't like this algorithm is really not specific at this point. We don't know what is the projection about. So we will define this notation. I start from X, do a gradient descent with this step size, right? And then I do a projection step. This is like starting from X and run this projected gradient descent algorithm for one step. Okay, and I denote the new update parameter as X plus. Okay, just like this is like XK. This will be XK plus 1, right? So I simply define this mapping for convenience. And then I also define GCX to be 1 over step size multiplied by X minus X star. Why do I want to do that? This is defined as this one, right? And you plug in the definition of X star. I use a bracket instead. This is the definition of X plus. You can see that if this is a generalized kind of generalized gradient, because if the projection if there's no constraint, right? If this constraint is simply the entire space, meaning that if there's no constraint, then this projection operator simply is an identity operator. It simply preserves this point. In that case, we can just ignore this one. Projection is simply this point. And you have X minus X plus this one. X minus X cancels out, eta cancels out. So GCX becomes the gradient. Okay. If there's no constraint, this definition is simply the gradient, right? So if there is a constraint, then this GCX is simply a generalized definition of gradient in the constraint case. Okay. We introduce this definition just to conceptually it is like a gradient in the constraint case. And so this GCX is like a generalized gradient. Yeah. So this GCX generalized gradient in the unconstrained case, right? And it also obeys the similar property. In the unconstrained case, we know at X star, at the minimizer, the gradient is 0. Right? But in the constrained case, right? If you constrain, in the constraint case, if you constrain your variable within this interval, you can see at the minimizer, the gradient may not be 0, right? The gradient is not 0 because you have a constraint. But in the constraint case, if you refer to this definition, then we have GC X star. And at the minimizer, this GC X star is 0. So this is a proper generalization of the gradient in the constraint case. This is a very interesting concept. Once you introduce this definition, you can sort of understand this constraint problem, similar to an unconstrained problem. The main result is to show that for any point x and for any minimizer x star of this constraint problem, the following inequality holds. This is an inequality about the generalized gradient. Okay. It's GCX dot product with x minus x star can be lower bounded by these two terms. And this dot product term, we have seen it in many cases, because it is basically, in this case, it is basically equals to GCX minus GCX star dot product with x minus x star, right? Because this is 0, this one is 0, right? So this term basically characterizes the correlation between x minus x star and the GCX minus GCX star. So it's like a fundamental property about this mapping, generalized gradient mapping GC. In the previous lectures, when we talked about the strongly convex functions, we have a lot of equivalent definitions that takes a very similar form, right? It's the dot product between the gradient and the x minus x star. Here's the same idea, but we simply replace the gradient by this generalized gradient. Now, suppose we can show this inequality, then the convergence guarantee is just one step. Then the convergence guarantee is just one step. You just follow here. You just follow the convergence analysis of gradient descent. Okay, let me just look at this one. I did not include the detailed proof here, but I think it's just a direct expansion of the distance term. Okay, maybe I just quickly mention the proof. Okay. Okay, we start from the second-hand side, the left-hand side. Now, what is xt plus 1? Now, go back to the by the update rule, right? It's projected gradient descent. So it's xt minus eta gradient of xt minus x star. Right, and I want to introduce something like this. Okay, so let me put it here. I can write it as xt Okay, so maybe let me do one more step. Based on this definition, I can rewrite the update rule of projected gradient descent as xt plus 1 equals to xt minus eta gcxt. Yeah, this is an alternative expression for the projected gradient descent. But just plug in the definition of GC, you will recover the projected gradient descent update. Okay. So here, xt plus 1, I just replace it with this one. Okay. Let me just ignore this one. So just xt minus eta gcxt minus x star. And this is a quadratic term, so you can decompose it. So it is equal to xt minus x star square. Okay. No, plus eta square gcxt square. And minus the two cross terms, 2 times xt minus x star. There's a eta here, gcxt. Okay. And this dot product term, this term, okay, you can use this inequality to get an upper estimate of this inner product term, okay? Because there's a negative sign. Right? So you apply this inequality, you can upper bound this inner product by those two distances. And then those two distances can be combined with these two. Okay. Eventually, you will see, you will end up with a recursion, very simple recursion. It's a contraction. And then you will have a linear geometric convergence. Okay. So it's a very simple step. So I will not write down all the details. So the key here is to prove this key inequality. Okay. So it remains to justify 3.3. 3.3 is this key inequality. Okay. So we can start from this series of inequalities. We know fx plus minus fx star is bigger than 0 because fx star is the minimum function value. So you pick any other point, the function value is bigger. Right? So this is a trivial inequality. And then I can introduce a trivial term. I subtract fx plus fx. That doesn't really change anything. But now by introducing this term, I have two different terms. I can bound them separately. For the first difference term, fx plus minus fx, I use the smoothness condition because f is smooth, so these two can be bounded by the inequality on smoothness. And on the other hand, F is strongly convex, so I can use strong convexity to bound the second term. And then I just combine all these terms together. Now what we can see is this. So first of all, these two dot product term, they are combined together and we get this one. This x, negative x cancels with x. So we get this term. This term is by definition x minus x plus is eta times GC, right? So use this one, we have GC, and eta is just 1 over L. So plug it in, we get this term exactly, right? And the last term is preserved, minus mu over 2, the distance squared. Okay, and this is already very similar to this inequality. You know, we have these two distant terms, we have this dot product. So, but there's something different. Here is we only have a gradient, not GC. So this inequality would establish 3.3 if we can show the following inequality. Okay. If we can show this one, just plug this one into here and rearrange the terms, then we are done, right? So we just need to show this inequality. And this inequality tries to bound this dot product term, which is here, by another inner product term where this gradient is replaced by the generalized gradient. Okay. So basically, if we replace gradient by the generalized gradient, the dot product will only be bigger. If we can show this, then we are done. And moreover, this dot product term is equal to these two terms. Okay, so the logic is that if we can show this one, and this one is equal to these two terms, now you replace this dot product here by these two terms, that will give us the desired result. Okay, so the only thing we need to justify here is to prove this inequality. And for this inequality, you just rearrange it. You move the right-hand side to the left, combine all the terms. It will be equivalent to the following inequality. X star minus x plus minus x star is here. Now GC, you can replace it by these terms, right? GC equals to x minus x plus equals to this projected gradient descent step, right? You just put everything into here, you will get this expression. So we need to show this inequality. And this inequality actually can be proved directly from 3. Or this directly from this. Okay, this is directly coming from 3.4. right? So there's nothing new here. We just move this term to left hand side and use all the definitions. And so all everything left is to show this 3.4. Okay. Now 3.4. Okay, so this is a generalized version of 3.4. Okay. It says that for any y in the set C, we have this inequality. Okay. But 3.4 only specifies y as x star. Okay. So I think we will prove this generalized version and then we are done. Just let y to be x star. Where did I put this proof? Let me just quickly check. Yeah, maybe I removed it from the slides for some reason. Maybe the proof takes some time to establish. But let me, okay. In that case, so let me, okay. Then I think I will put it here for now, and maybe I will prepare for it next time. Maybe it takes several pages to establish this lemma. But essentially what this lemma says is that, and this is an abstract inequality. Left hand side is gradient f multiplied by x plus minus y. Now y is any point in the constraint, and x plus is defined by starting from x and do one projective gradient descent, and you can get to x star, x plus. And the right hand side is to replace the gradient by the generalized gradient. Okay. And this inequality says the left hand side is always less than equal to the right hand side. Yeah. Okay. Let's skip this this part here. So this is a result that is very useful, and we will use it several times in the subsequent analysis. But I think the proof is not very simple. It's not that simple. So with this tool, then we can easily get this result. It's just so then this inequality directly holds, and we can just replace this term by the right hand side, and the right hand side can be further decomposed into two terms, and that will give us the final result. Okay, so this will prove this key inequality, and with that, we can have the. It's very easy to establish the convergence rate. So this type of inequality is very we will see it very frequently in many analyses. It basically characterizes the correlation or the dot product between your update direction and x minus x star. This is your update direction, and this is x minus x star. Right? Because the projected gradient descent can be rewritten in a gradient descent form. This is like a gradient descent update, but GC here is defined by this definition. Okay, well, x plus is defined in this way. So you can rewrite projective gradient descent in such a gradient descent-like form. And then from here, intuitively, you can view GC as a kind of a gradient update, but only applies to the constraint case. Okay. And this key inequality is to characterize your update direction, the correlation between your update direction with x minus x star. Right. So say this is your current x, this is your target x star. So x minus x star is more like this direction, right? And your update rule is following the negative GC. Okay. So let's say this is GCX, then the negative GC will be here, right? So I mean the negative update direction will be pointing towards x star. Yeah, maybe I should show a better arrow. So let's say this is your GC, then right. Then your negative update direction will be pointing towards your x star. Right? If you can show these two is positively correlated, that simply means your update direction is pointing toward x star. Okay, and so this is the result for strongly convex problems. But for convex and smooth problems, we also have a different convergence guarantee. If we drop strong convexity, we can only show that the objective value decreases at a sublinear rate. This is like something 1/t. The numerator are all constants. Okay. So this is similar to gradient descent applied to convex and smooth problems. Right. So it's similar as the unconstrained case. And the proof is very different. In the unconstrained case, we follow the following 3 steps to the proof. We first show that the function value is decreasing, and then we bound the gradient norm using the function value difference. And lastly, we combine everything to establish a recursion on delta t. Okay. But in the constraint case, we can kind of follow in the similar logic, but the modification is a little bit tricky. And again, we will define GC in the following way. So this is like a generalized gradient, and we will show again in the constraint case, we will show that the objective value is still decreasing, but now the gradient is replaced by the generalized gradient. Okay. In the unconstrained case, we have gradient here, but now it's the generalized gradient. And then in step 2, we will bound the norm of the generalized gradient using the function value difference. Okay. And here's t+1 instead of t, but after that, when you combine these 2 steps, we will establish such a recursion. Okay. And in this recursion, here is delta t+1, whereas in the previous recursion, we only have delta t. But this will not lead to a significant different result. they are more or less the same. So you can see on the big picture, it's just replacing the gradient by the generalized gradient in a proper way. Yeah, and I think to prove all these results, so we need the following key lemma. Suppose F is convex smooth, and for any 2 points in the constraint set, we define the following points. Okay, X plus is starting from X, I do one step of projective gradient descent. Right? Because X plus is a subsequent up point of X. And then GCX is the generalized gradient defined based on X and the X plus. Okay. So then we have 3 points. We have X, Y, and X plus. We have 3 points. And this inequality says that these 3 points satisfy the following inequality. Fy is always lower bounded by these terms. Well, y, here xy could be anything in the set. X plus is related to x. Okay. Then when we apply this inequality, we just need to specify x, y, and x plus by following these conditions. This is a very general result, holds for any point x, y, and the corresponding x plus. Yeah. So let's look at how we can use this result to prove the previous key steps. To prove step 1, I just set x equals to y equals to xt. Right? X equals to y. So this is xt. This is xt. Now this term is gone because x equals to y. Right? So this is fxt. Now x plus is simply xt plus 1 because x is xt, right? So this is simply xt plus 1. And then you have fxt bigger than fxt plus 1 plus this quadratic term. And then you just rearrange the terms. You can get this result. This is exactly what we have in step 1. In step 2, to prove the result in step 2, we simply set x to be xt and y to be the minimizer x star. Okay, you put this into here, you can get this inequality. Okay, this is y, this is x plus, right? X is xt, so x plus is xt plus 1. And then you have the rest of the terms. And then I can simply drop this term because this is a positive term, right? So I can say greater than or equal to the dot product. I can drop this positive term. Once I drop this positive term, I can further, for this dot product term, I can just lower bound by using Cauchy-Schwarz inequality. Right? So in the end, this one, the norm of this one can be controlled by the difference of function values. Okay, so this proves the second one. Yeah, and yeah, maybe next time we will go into details so we can further show that the distance is diminishing. So we can further replace xt minus x star by x0 minus x star. Right, so this completes the proof for the second step. And then the last step is basically combining step 1 and step 2. Combining those two, we can establish this recursion. Okay. And so the key is to prove this very general result. Okay. And I think here I did not include it. Oh, I think, yeah, we have the proof for this result. So maybe we can go over this part next time. Okay. So let me know if you have questions about homework 2. It is due next Friday, I believe. Okay.
Practice work 2.